Welcome to this engineering mechanics lecture. In this lecture, we will speak about forces and their actions on structures. Let's first consider what a force is. If we want to stick a pin into a wall, we need to apply a certain force in a certain direction. As a result, force has magnitude and direction. The direction of the force is defined by the line of its action. What does a force remind us of? Force has magnitude and direction. A vector has magnitude and direction. Therefore, a force is a vector. Now, let's consider a few elements of vector algebra. Two vectors can be summed in the following ways. The first way is based on positioning the vectors heads to tails and connecting the tail of the first vector and the head of the second vector. The second way is based on positioning the vectors tail to tail and drawing a parallelogram. The longest diagonal in the parallelogram is the sum of the vectors. Several vectors can be summed using the heads to tail rule as follows. The sum of vectors is obtained by connecting the tail of the first vector and the head of the last vector. The sum of these two vectors equals 0. And that's because these vectors are parallel, equal in magnitude, and opposite in direction. The sum of these vectors is also 0, because this system of vectors has the same starting and ending point. This kind of system of vectors is called a closed system. A vector has magnitude and direction, as we said. These two features are independent. Let's consider how to divide between them. This can be done by introducing a vector of unit length in the direction of the original vector. As a result, any vector can be described by the magnitude and a unit vector giving the direction. Usually in literature, vectors are described by bold capital letters, magnitudes of vectors by italic letters and directions, or unit vectors by bold small letters. We'll use this notation in the lectures. Any number can be represented by a sum of two other numbers. Similarly, any vector can be represented by a sum of two other vectors. If we select two known orthogonal directions, x and y, vector A can be represented as a sum of two vectors in these directions. The vectors ax and ay are called the components of vector A. Additionally, we can select two unit vectors, I and j, in the directions of x and y. Vector A can be represented as the sum of the magnitudes of the vector components with their corresponding unit vectors. The directions of two unit vectors I and j are the directions of the x and y axes. To find the magnitudes of the vector components ax and ay, we define the angle theta between the direction of vector A and the x-axis. The magnitudes of the vector components ax and ay can be found as follows. Ax equals a cosine theta, and ay equals a sine theta. The angle theta can be found using the triangle shown at the bottom right as an arctangent of ay divided by ax. And the magnitude of vector A equals the square root of squares of ax and ay. Consider vector C to be the sum of vectors A and B. Therefore, the magnitudes of the components of vector C in the x and y directions can be presented as sums of magnitudes of the components of vectors A and B in the x and y directions. The components of vectors A and B can be presented using vector magnitudes and inclination angles to the x-axis. Since force is a vector, the rules of vector algebra are applicable. So force F can be divided into components in the x and y directions, which can be presented using the force magnitude and inclination angle to the x-axis, as shown here. If the components of the force are known, its magnitude can be found as the square root of squared components. Now let's consider a coplanar system of forces. They can be divided into concurrent and non-concurrent. In the concurrent system of forces, the lines of actions of all forces intersect at one point, while the non-concurrent system of forces does not have such a point. A special case of non-concurrent system of forces is a system of parallel forces, where the lines of actions do not intersect. Similar to vectors, the sum of several forces can be found using the heads to tail rule. The obtained force is called the resultant force. The external effect of a system of forces on a structure can be substituted by the external effect caused by the resultant force. The components of the resultant force can be found by summing the components of each force in the system considered. If we consider a system of two forces, the components of the resultant force can be found using the angle of inclination to the x-axis as given here. Forces can push or pull. Here you can see that this force is pushing a book. In addition, a force can turn an object around a certain point. If we apply force to a spanner attached to a nut, the spanner with a nut will turn around a bolt as shown here. The rotating action of the force is called moment. The magnitude of the moment is found as the magnitude of the force times the shortest distance between the considered point of rotation and the line of action of the force. Let us now think whether a moment is also a vector. We established that a moment has magnitude. Let's consider if a moment has direction. In the example given here on the top right, we can see that the moment is rotating clockwise. If we change the direction of the force, the direction of the moment changes to counterclockwise. Therefore, a moment will rotate in a certain direction. A positive direction of moment in a right-hand coordinate system can be shown using a screwdriver. The screwdriver points in the positive direction of the moment when it's used in your right hand for fixing a screw. The symbol of a moment is usually a vector with a double arrow, as you can see here. Let's consider a right-hand coordinate system with a force in the xy plane acting in the way shown on the slide. Take point O on the right from the line of action of the force. In this case, the force will rotate around the point O with a counterclockwise moment, and the direction of this moment is in the positive direction of the z-axis. Note that unit vectors I and j and k define the directions of x, y and z axes. In the right-hand coordinate system, the counterclockwise moment in the xy plane will be positive because it will be in the positive direction of the z-axis. On the other hand, clockwise will be negative. As discussed earlier, the sum of a system of forces gives the resultant force. Accordingly, the sum of moments produced by forces of this system around a certain point is the resultant moment. The magnitude of the resultant moment is the sum of magnitudes of the moments generated by each force. Force times distance. Let's consider a force F acting vertically downwards as shown on this slide. Let's take a point, O1, at a distance of A on the left from the line of action of force F. The force will generate a moment around O1. The magnitude of this moment equals the magnitude of the force times the distance A. As you can see, this force rotates clockwise around O1, so the moment is negative. Now we take a point O2 at a distance B on the right from the line of action of force F. The force will rotate counterclockwise around O2, generating a positive moment with a magnitude F times B. The moments produced by the force around O1 and O2 are not equal, since the distance A is different from the distance B. In addition, the moment rotates in different directions. Let's now consider a system of two parallel forces with equal magnitudes acting vertically downwards and upwards as shown on this slide. Here we'll take point O1 at a distance A on the left from the line of action of the left force. The moment produced by the two forces around O1 equals the magnitude of the force times the distance between the two forces. The direction of this moment is positive. Let's now consider point O2 at a distance B on the right from the line of action from the left force. The moment produced by the two forces around the point O2 also equals the magnitude of the force times the distance between the two forces, and the direction of this moment is also positive. As a result, we can see that a system of two parallel, equal and opposite forces produced the same moment at two different points on the plane. Since points O1 and O2 were selected at random, we can conclude that the moment produced by a system of two parallel, equal and opposite forces is the same at every point on the plane and equals to the magnitude of the force times the distance between the two forces. This type of system is called a force couple, or a coupled force. A force couple is characterized by the fact that it applies the same moment at every point on the plane. This is a very important system of forces in structural design. Throughout the degree, you'll meet force couples in the design procedures of many different structures. In this lecture on forces, moments and coupled forces, we have covered some of the really basic concepts in engineering mechanics, which will accompany you throughout your engineering career. I hope you understood them all, but please ask if you have any questions. And please join me for some tutorials where we'll exercise everything that we discussed here. See you later, and bye for now.